Okay. Hi, good morning, everybody. Welcome to the ECE Colloquium. My name is Mariam Fazel. I'm a professor in ECE, and I oversee the Colloquium series this quarter. We have an exciting lineup of speakers this quarter. Please check the Colloquium website for the full schedule. You can ask questions at the end of the talk. Please use the raise hand feature of Zoom. And for those of you who are taking the Colloquium for credit, I just wanted to mention it's based on your attendance of the seminars on Zoom. For details, please see the course Canvas page. And I'd now like to ask Arka to introduce our speaker.
Thanks, Mariam. I am Arka Mujumdar. I'm an assistant professor here at University of Washington in electrical and computer engineering and physics. And today it's my great pleasure to introduce Dr. Sonia Buckley. Dr. Sonia Buckley is a physicist at the National Institute of Standards and Technology, known as NIST, in Boulder, Colorado. Sonia received a PhD in applied physics and master's in electrical engineering from Stanford University in 2014, and also her undergraduate degree in physics from Trinity College, Dublin in 2009. Her doctoral work was done under the supervision of Professor Yelena Vukovic at Stanford University on nonlinear frequency conversion in 3-5 photonic crystal cavities. Our current research interests are in the integration of optoelectronic devices with superconducting electronics for application in integrated quantum optics and artificial intelligence. And I also like to mention that this talk is co-supported by Quantum X initiative at University of Washington campus. So without further ado, Sonia.
Thanks, Arka and Mariam, for the introduction. And for the invitation. Just so you know, I actually went to graduate school with Arka, who we were already calling Professor Majumdar at the time. So for any embarrassing stories, or if you have any, or for any questions you have about my talk, you can email me at sonia.buckley@nist.gov. So I'm, like Arka mentioned, I'm a physicist at NIST. I work in the group of Rich Miran and Seiwu Nam. And Arka asked me to give this talk on quantum optics or engineering. And so what I've mostly worked on has been the technologies for quantum optics, more than doing quantum optics experiments myself. So that's what I decided to talk about in this talk. Hang on, my slide isn't, there it goes. So, so that's the motivation, is that we actually need to develop key components if we want to bring quantum optics to an integrated platform. And what I mean by that is if we want to bring quantum optics on chip. And then if we develop these technologies, I'm not going to talk as much about that in this talk, but if we develop these technologies for integrated quantum optics, they will have applications beyond just quantum technologies. You never know what technologies will be useful for in the future. So to start with a little bit more motivation, I'm just going to give an example of a large quantum optics experiment that was done in 2015 in our group at NIST. And that was one of 3 loophole-free Bell tests that was done this year. So for those of you that don't already know about what a Bell test is, you don't really have to worry about it for the rest of the talk. But just a reminder for those of you that kind of have an idea, basically you have a photon, entangled photon source at the source, and you send a photon to a distance station at Alice and one at Bob, and then you make you randomly choose a polarization basis to make a measurement of those photons at both Alice and Bob, and then basically based on the correlations between those photons, you can rule out a classical explanation, essentially. So the Bell inequality essentially you basically can't explain the result of the Bell test classically. Loophole free, but just means that you have to make certain assumptions about your experiments, and they call those assumption loopholes. So you can see on the right there's a schematic of the building at NIST where the experiment was done. And you can see that the distances are, over 100 meters. So the distance between the source and Alice and the source and Bob. So this was a large experiment. And the reason for that is you need to, you need to be able to make your measurement in order to, you need to make the measurement faster than light can travel from Alice to Bob. And so I'm going to zoom in on the source part of this experiment here so you can get a better idea of what that looked like in this experiment. So, this is kind of a complicated schematic of the source. I'm just going to point out this nonlinear crystal, and then this is what the optical table actually looked like. So this was in 2015 what the source in that Bell experiment looked like. And I point out the nonlinear crystal here. And so you can see it's a pretty big optical table. So the motivation behind what I'm talking about is to take an optical table that looks like this for a quantum optics experiment and shrink it down to the size of a chip. And there are reasons to do this beyond just making it smaller. So another reason you might want to do this is this experiment took a huge amount of work to align and constant work while it was running to make sure that it stayed aligned, because the light is steered by mirrors and other bulk optics components, and these all have to be aligned. A second reason is if you want to scale up this experiment. Suppose you think of a quantum optics experiment that requires 3 Bell tests. Well, now you essentially need 3 of these tables. Whereas if you have it already on chip, you just need 3 chips. That's you just refabricate the same chip 3 times. So you can also scale up to much larger experiments, much more complex experiments if you can bring everything down to the integrated scale. So then here are just some other examples of large quantum optics experiments that could benefit from being brought down onto the to the chip scale. A random number beacon. This is something that the group that did the Bell test at NIST has been extending it to become a source of certified random numbers. Boson sampling is another thing that's already more or less mostly being done on chip. And then you can do things like multi-photon quantum state generation and linear optical quantum computing. All of these are large experiments that really, if you want to, that will really benefit from being brought down to the chip scale. Okay, so then what do we need to do to bring a quantum optics experiment onto a chip? Well, I'm going to talk about that in sort of 3 broad categories that most experiments can be broken down into. And these are the detectors, the integrated optics, and the sources. And I'm going to explain each of these one at a time and sort of give an overview of our work at NIST on these, or at least the work I've been involved in at NIST in these 3 broad categories. So the first is the integrated optics. So what I mean by integrated optics are waveguide devices for guiding and manipulating light on chip. And these can be things like beam splitters, it can be filters, optical filters, and things like polarization optics, polarization rotators and filters, and a whole host of other things as well. So the waveguide is the primary component of on-chip integrated optics, and just a reminder for those of you who who forgot or never knew, you essentially have a core with a higher refractive index surrounded by a cladding of a lower refractive index. And if you do this, you can guide light in a mode, and the scale of this thing can be anywhere from hundreds of nanometers to hundreds of microns. So the first thing you need to do for your quantum optics experiment is select a material platform which you're going to be using. And so there's a lot of things that go into that decision. Things like, what is your operating wavelength? Your material obviously needs to be transparent in your operating wavelength. Are you going to be integrating it with electronics, for example, or active materials. Do you need an active material? For example, do you need modulators on chip? Nonlinear optics, a lot of quantum optics experiments use parametric down conversion as a source, which requires a nonlinear optical material. How big can it be? What's your loss tolerance? And what's your loss tolerance for coupling on and off chip? And so, unfortunately, a lot of the time, these things come in trade-offs. For example, the lowest loss waveguides are also usually the biggest waveguides. And a lot of the time, if you want to integrate with an active material or integrate, you're using a higher loss material as well. You may be using a smaller waveguide size, and now on and off chip coupling is harder and has higher loss. So all of these things go into your decisions when you're deciding on a material platform. And then what are the kinds of materials that we're talking about? Well, we're talking about things like crystalline silicon. And then there are also deposited materials, things like amorphous silicon, silicon nitride, and other deposited dielectrics. They can be things like 3,5, so gallium arsenide, gallium phosphide, indium phosphide. Other things, laser-written glass waveguides, and then a whole host of other materials, things like diamond, lithium niobate, aluminum nitride, and a whole bunch of other materials are also possible. But I'm just going to choose 2 material platforms that I've been involved with to talk about today, and you can just bear in mind that there's a whole lot of other materials of interest. So the first is silicon on insulator. So silicon on insulator is essentially you take a bulk silicon wafer, you grow thermal oxide around 3 microns on it, and then they wafer bond thin film of silicon. Usually for telecom wavelengths, you use around 220 nanometers tall. And then you can make waveguides in it. So your high index material is silicon. Silicon is transparent from around 1.1 to 8 microns. Typical losses in the telecom are around 3 dB per centimeter. And the typical size of a waveguide for 1.5 microns would be about 400 nanometers wide. And you can do bend radiuses of around 3 microns. This is an important one. There are specialized foundries available. So you can send your design to a foundry and they'll make it for you, and process design kits and so on are available too. You can dope the silicon and make active devices, things like modulators. Light sources are pretty hard in silicon, but I'm going to talk about a silicon light source that we've been working on a little bit later in the talk. It has a high nonlinearity, so you can do some kinds of nonlinear optics in silicon. And like I said, it has compact size. So this is just an image of from AIM Photonics. AIM Photonics is a foundry specifically for photonics in silicon on insulator. You can pay per wafer, and then you can have your device designs fabricated there. So that's a big advantage of silicon on insulator. If you work on it, you don't necessarily have to fabricate it yourself in the clean room. What are the kinds of devices people make in silicon on insulator? And examples are ring resonators, things like beam splitters where light comes in here and is split in 2, gratings for coupling light into and out of the waveguide. And then those are passive devices. Then active devices, things like modulators. Here's a ring resonator where you can inject carriers and shift the resonance of the ring, and that can act as the modulator for light waveguide. And then this is an example of one of the light sources that we built that I'm going to talk about later. So this is an example of a device that we made in silicon on insulator. Essentially, light comes in here through this input grating, passes through this waveguide. It's split in 2. This is a beam splitter, 50-50 beam splitter, a second 50-50 beam splitter, a third 50-50 beam splitter, and light is essentially divided equally in 8 parts. You can couple it out through this output grating, or it can be measured on one of these 7 detectors. And so, so the detectors, which we use here, are actually superconducting detectors. And these operate cryogenically. So we need to actually be able to couple light into these waveguides in the cryostat. And that's actually a pretty challenging problem. It winds up being really hard to couple light into a waveguide in a cryostat. And we're interested in doing cryogenic fiber packaging. This is a scalable and cheap, easy way to do it. And this is the first way that we've developed. And so here we have a grating in a silicon waveguide. So light comes in here and couples into this waveguide. This is an SU8 collar that we fabricate. This SU8 is a polymer that's around 50 microns tall. So you align the fiber into this collar to the grating. You align your two fibers, then you glue them down, and you glue them to this aluminum package that we also made. And then you can just put it in the cryostat and start your measurement. So we've cooled these below 1 Kelvin with only around 1.5 dB of additional loss. But we're working on a second generation. Unfortunately, the grating couplers we've made so far haven't been really efficient. So we're getting, at best 6 dB of coupling loss, which as you'll see in a minute, isn't really good enough for a lot of quantum optics experiments. So we're working on this next generation of fiber packaging. So here we make a tapered optical fiber. In this case, the taper is made by dipping the fiber in HF and letting it evaporate. And then we coat the tip of the fiber with a higher index material, in this case, SU8. The reason being that if you want to couple to a waveguide that has oxide on top of it, you can't use an oxide fiber. You need something with a higher index. And so this couples to a tapered waveguide on chip, and we get around between 1 and 1.5 dB of transmission loss. And this is also epoxied down and packaged. This paper is all at room temperature, but we've made really good progress cryogenically recently as well. And this is critical if you want to use these superconducting detectors, which is what I'm about to talk about in a minute. But first, I want to mention a second material platform, and that's the deposited dielectric platform. And the reason you might want to use this, one reason you might want to use this is you can actually deposit these waveguides on top of another chip. That's what I mean by back end of line compatible. You can put it on top of a fabricated chip. And one of the main reasons that it's back end of line compatible is you do everything with room temperature deposition. So you take your wafer and you deposit silicon dioxide on top of it, and then you deposit your waveguiding layer on top of that, which can be amorphous silicon or silicon nitride, and then we can deposit our superconductors on top of that, and then this is our collar layer, which we use for the original packaging scheme. So using these deposited dielectrics, we were seeing, this is a ring resonator we fabricated in silicon nitride. It had a Q of around a little over 100,000, which corresponded to losses of around 2.5 dB per centimeter. And the reason for even this higher loss was basically that the precursor that you use to deposit this film has hydrogen in it, and this hydrogen gets incorporated in the film, and there's an absorption peak around telecom wavelength from this hydrogen, and that causes a problem. So one of the scientists in our group actually came up with the idea of using an isotope of hydrogen, deuterium. So hydrogen has a nucleus that's a single proton. Deuterium has a proton and a neutron in it. So if you use silane with deuterium in it as your precursor, then you shift the absorption peak in the deposited film to much longer wavelengths, and you can wind up with propagation losses as low as 0.2 dB per centimeter. So you really reduce the losses that way. We've also fabricated detectors on top of the silicon nitride film. So here you're seeing a device where there's, again, an input grating. Light comes in here. It can couple through one of these rings and is dropped at one of, at a detector, and this happens at 4 different detectors. and you can see if you scan the wavelength of the laser that you put in, you can very clearly see the ring resonator response in the spectrum. So what's another good thing about these deposited dielectrics is that you can actually stack them. You take your first deposit dielectric layer, and then you can etch your waveguide, deposit silicon dioxide again on top of that, polish it down, and then you can deposit more layers of waveguides on top of that. And you can get transition losses as low as, I think we got 0.05 dB per transition between layers, so you can couple light from one layer to the next. You can also get waveguide crossings I think with losses in the tens of milli dB. And so we can make these in amorphous silicon or silicon nitride again. And what you might want to do with this in bringing it back to our quantum optics experiment is you might want a low loss dielectric layer for low transmission loss, and then you might want to transition to a silicon or 3-5 waveguide for your active photonics if we're doing nonlinear photonics with. Okay, so then there's a whole bunch of other materials that I'm not going to talk about it, but I'm just going to mention so that you know that's not the be all and end all. 3-5s are excellent light sources, and a lot of progress has been made in wafer bonding 3-5s on insulator. In our group, you can check out this paper, but there's been other papers from other groups as well. Then there's laser-written glass waveguides. These are actually the lowest loss platform, and they have very low on-chip coupling loss. It's hard to make active components in them, and they're a lot bigger. So the silicon waveguides are on the order of hundreds of nanometers wide. These are hundreds of microns wide. And then all kinds of other materials and hybrid platforms are also possible, which I know a lot of people at UW also work on. So then let's just bring this back to our Bell experiment example. So in the Bell experiment, currently routing is done with hundreds of meters of optical fiber, and the total transmission loss to that fiber is around 0.05 dB. And in the Bell experiment, in order to close the detector loophole, the total losses can't exceed 1.8 dB. So bringing that back, a silicon waveguide has 3 dB per centimeter loss. So you better not have more than a centimeter of silicon. You better not have a centimeter of silicon waveguide in there. And if you remember, our grating coupler losses were many dB. So you really need to bring the losses down for this experiment. And then also, it's going to be required to integrate with nonlinear materials. They use a spontaneous parametric down conversion source, for example, in the current Bell experiment. Okay, so I'm going to switch now to talking about the detectors, which I've already briefly mentioned and showed you some examples of, but let's dig a little deeper into that. So what do you need in a detector? So you usually, for almost every quantum optics experiment, you need single photon detection with high efficiency. If you want to use silicon waveguides, you need the wavelength of the light. You need the wavelength of the light you're using to be higher than 1.1 micron or longer than 1.1 micron. So that means your detectors have to be sensitive out there. And if you want to use low loss optical fiber transmission, you want them even longer at 1.55 micron. The typical detectors people use are silicon APDs. These only actually work above the silicon band gap for the same reason that you want the wavelength to be longer than 1.1 so that you can transmit it on silicon waveguides. Is the same reason that silicon APDs don't work. They need to absorb the light in order to detect it. So we're going to talk about superconducting detectors because these work in these wavelength range as well as being fast and efficient. Specifically, we're going to be talking about superconducting nanowire single photon detectors. So how these work is you deposit a thin film of a superconducting material and you pattern it into a narrow wire. You bias this with a bias current. When a photon hits, it breaks Cooper pairs in the superconducting film and generates a hot spot that is that's not superconducting. And then the current diverting around the hot spot, it increases the current density everywhere else, keeps it up, and you basically get this normal region in your wire where the whole width of the wire turns normal. And now all of a sudden you will go from zero resistance to some resistance. You develop a voltage across it, and you can detect that voltage. And then the hot spot cools off and you reset it to the original state. What are the specs of these? Well, with these detectors, you can get, our group has gotten total system efficiencies of up to 98% at 1.55 microns. You can get temporal resolution or jitter as low as 3 picoseconds, although tens of picoseconds is more common. You can see count rates of up to 10 megahertz. You can get wavelength sensitivity from 350 nanometers all the way to 10 microns. And then kilopixels array with over 99% yield have been demonstrated. The one thing is you need a cryostat. So they operate, depending on the material, you can either operate them at 4 Kelvin or for the ones that we use, you need to operate around 1 Kelvin. So I mentioned that you can use these detectors from 350 nanometers to 10 microns. So if you have but you can't necessarily use the same nanowires for all of that range. So for the narrowest nanowires, if you have a low energy photon hitting it, the hotspot can grow to the width of the nanowire. If you have a wide wire, however, the hotspot might not grow to the full width of the nanowire, and so you don't measure resistance. Higher energy photon, on the other hand, is able to deposits more energy and is able to make a hotspot grow to the width of the nanowire. So essentially, the longer the wavelength you're working with, the narrower the wire you need. So then this is what a typical nanowire detector looks like. So the white region is the actual detector, so you can see that you coil it up on itself in order to collect more light from an optical fiber mode. And then you can see that the wire width is around 100 nanometers. So when you get one of these detectors, this is what accounts versus bias curve for one of these detectors should look like. So as you increase the bias current across the detector, you suddenly start detecting photons. You maybe won't detect every photon, but as you increase the bias current, you detect more and more of the photons. And eventually, it starts plateauing because you're detecting every single photon that's getting absorbed by the detector. And this is where you want to operate because this indicates you're in a region of maximum quantum efficiency. And also, you can bias it, let's say, here at 7 microamps. And if your current source is at 7.2 or 6.8, your efficiency won't change. So you can bias it here very stably. So in the Bell experiment example, superconducting nanowire single photon detectors are already being used at the end station. So here at Alice and Bob, they're both cooled to 1 Kelvin, below 1 Kelvin. And the original detector efficiencies were around 90 and 92%. I think the setup has been upgraded and now they're closer to 98%. And everything I'm talking about has been fabricated in the NIST clean room. Here's a picture. But we do ultimately want to move to a lot of our fabrication to a commercial foundry where other people can take advantage of designs and use a process design kit and so on. So at NIST, one thing is we do have both a Joule 1600 e-beam writer and a photolithography tool. If you use the photolithography tool, in practice we can make the 100 nanometer wires with the e-beam tool very easily. But everything is even easier if you can use photolithography. You can make larger area detectors. Integration is faster and easier. And so one thing that we've done in our group recently is by varying the material of the detectors, we found that we can make wider wires that detect photons at 1550 nanometers. And this is big because it really helps with scalability if you can do everything with photolithography. And so you can see wires that are microns wide can actually detect these photons. Here you see counts versus bias current for a wire that's 2 microns wide. So let's bring it back to the typical nanowire detector. Like I said, that was 100 nanometers. We've moved to being able to make them wider if we want to for integration, and that's what we did with these waveguide integrated detectors. So if you want to detect light that's coming in on a waveguide, you basically put the detector on top of the waveguide, and now light that's traveling down this waveguide will be evanescently absorbed. This green is the detector, will be evanescently absorbed by the detector. And here's a cross section where you can see the optical mode, and we've drawn in the detector is in the evanescent field of the mode, so light propagating in this mode will be absorbed. And so I'm bringing you back to this this work where we have the device that splits light coming in through this grating evenly to 7 different detectors. And so you can imagine we could use these single photon detectors for some kind of multi-photon state characterization experiment. Or you can just use it to characterize the detectors, because each of these detectors is seeing the same amount of light, so you could vary parameters of the detectors. We've also made other devices. This is just one example of another device we've made. In this case, you put light in through this input grating, split into here, split into again, to 3 different, it's actually 3 different devices here. And each of these devices is, we call a high dynamic range array. So basically light coming in here, 90% of it goes to the first detector, 10% goes straight on, 90% to the second detector, 10% straight on. And the idea is that you can get an additional 50 dB of dynamic range using this. In practice, what we've actually used it to is to characterize the scattered light coming from here. We can measure how much scattered light we're seeing on these detectors. So the real question is, which quantum optics experiments are devices like these useful for, or do they work for? And it really depends on if we can get the insertion loss low enough. You know, the packaging problem, it doesn't seem that interesting, but it turns out a lot hinges on it. Because things like higher photon number states will actually look like thermal states in the presence of too much loss. You know, things like the Bell experiment require the loss to be low enough. And it's just, quantum is hard, and you know, there may be other classical applications that are more tolerant, and I'm going to just present 1 or 2 slides on that at the end. But really, it all hinges on getting the losses low enough. So where are we with respect to the
one thing, can you come close to the phone again? I think you are kind of dropping off a little bit.
Okay, I'm
Yeah,
sorry.
thank you.
Yeah, so if we bring it back to the Bell experiment example, we're already using fiber-coupled superconducting detectors. To switch to waveguide detectors, we're really dominated by the insertion loss, and it's not really good enough yet. If we could move both detectors onto one chip, we would significantly reduce the equipment overhead. Like I mentioned, there's a separate cryostat and associated equipment at each of these end stations. Okay, then the final component I'm going to talk about are the sources. So at least in my opinion, the sources are the most challenging element. And so what do we need from a quantum source? So on the right, I've shown here a coherent state with you know, a certain average photon number. A single photon state would look more like this, where you have you know, a probability of 1 of getting 1 photon rather than you know, a probability of getting different photon numbers. But you might also want other quantum states, things like entangled photons and so on. You might have some kind of speed requirement if you're doing something like quantum key distribution or random number generation. You might need a certain number per second. Size, you might have some kind of size requirement. Efficiency, if you want your photons to do some kind of interference, then they need to be in the same mode, which we call indistinguishability. If they're not indistinguishable, the 2 photons can't interfere. You might need them to you might need to get the quantum state every time you push a trigger on demand. And then I'm going to talk about a problem with stray light too. So here again is the schematic of the source that was used in the Bell experiment. So there was a Ti-sapphire laser pump, and that pumped a nonlinear crystal for this process, spontaneous down conversion. So in down conversion, you pump with light of 1 energy, and then you generate for every photon at that energy, or for some of the photons at that energy, you generate 2 different energies of light that add up to that original energy. So how do you do that on chip? Well, you can't actually do that process in silicon. You can do it on chip with other materials. In silicon, what you can do is something similar, where 2 pump photons generate a signal and an idler photon, spontaneous 4-wave mixing. So to do that, you can pump with an off-chip laser, and then you can use a high Q microring resonator. You essentially set the laser to be on resonance with one of these resonances, and then you can generate correlated photons in adjacent resonances. The idler and signal will be in adjacent resonances. And then ideally on chip, you would have these filters. You need to get rid of this pump, which is going to be over 100 dB brighter than the idler and signal. And so you filter the pump out using these on-chip filters, and then you can send it to a beam splitter and to detectors to do your quantum state characterization. And so this experiment was done in a CMOS process. Was done at NIST. It was fabricated in a CMOS process. And you can see here that, well, the pair source and the filters were all on chip. The detectors were actually off chip. And one of the main reasons for that was, even though there were filters on the waveguide to filter out the pump light, there was so much pump light scattering around the chip that it dominated the response, would dominate the response on the detectors. And so the detectors have to be brought, the light has to be brought off chip to really get rid of the pump light so that you can detect the correlated photon pairs. And so that's actually kind of a big problem. I mean, it's only a technological problem. There's no reason it can't be overcome, and I'm sure groups will soon. But that is a problem. Another problem is that if you put these filters on chip, they all have to line up. You need multiple filters, and they need to line up with the pair source. And it turns out that the fabrication tolerances just aren't good enough that you can guarantee that. So what you wind up doing is fabricating a bunch of filters and then just finding the one that wound up working. Or you can put heaters on chip to tune the filters. So you wind up if you want to scale this experiment up to have multiple sources, now you need, tunable filters at every source, which is again possible, but it's another layer of complexity and another challenge. Okay, so another option is to try to build an electrically injected source, because this actually eliminates the problem of the scattered pump light if you can electrically inject your source. And so examples of electrically injected single photon sources are things like quantum dots and emissive centers. So you essentially have a 2-level system where when an electron decays from an excited level to a ground state, you emit a single photon. So I've been working on emissive centers in silicon. And so the way that these silicon emissive centers work is they're very similar. They're an emissive center. They're a defect in silicon, and you make them by implanting silicon ions in a silicon wafer. And so they're similar to, let's say, a nitrogen vacancy center or something like that in diamond. They're a similar type of center. They're a trigonal symmetry center, and you can lithographically pattern where you want to put them. So you might have heard that silicon is a really poor light source, which it is, but it does turn out that at cryogenic temperatures, there are these emissive centers that will emit light. And so then here's a spectrum from an ensemble of these emissive centers in silicon. So you can see that the emission wavelength is at 1218 nanometers, and that the lifetime is around 30 nanoseconds. And these emissive centers operate below 40 Kelvin. And then more recently, we've actually coupled some of these emissive centers to ring resonators and then to waveguides. So you can see this is a in-gas camera where you can see light, the light from the emissive centers above the ring and also above a collection grating. But what I'm interested in talking about more here is electrical injection. So you can actually electrically inject and get light, waveguide coupled light out of these things if you implant the W centers in the I region of a PIN diode. So you put the W centers in the middle of a ridge waveguide, and then you forward bias the diode and you get light emission coming out along the waveguide. And then here's a cross section showing this brown region would be where the W centers are. And so then here's an optical microscope image of LEDs coupled to waveguides, coupled to these nanowire detectors, which we fabricated at NIST. And so you can see this is, if you take LED 1 and turn it on, you detect about 40 dB more light on the detector nanowire 1 than you do on the detector nanowire 2. And that's shown here in the optical length versus crosstalk plot. And we measured a total system efficiency of around 5 by 10 to the minus 7. So that's not, that's not a great efficiency, but we've done some work on photoluminescence and optimization of the design since then that suggests that we can do better in the efficiency. Although our second generation so far has only been a little bit better, a little under an order of magnitude better. But we have some ideas for how to improve that further. We want to bring this ultimately to a publicly available process. And so to start with that, we have a collaborator at SUNY Poly who has been helping us implant W centers in 300 millimeter wafers in their clean room. And so we did some, there's me standing with a 300 millimeter wafer. And then we characterized the cross wafer uniformity of the photoluminescence. And the next step now is they're actually working with us so that we can fabricate LEDs in their process. So they're going to do the electrical implant and the etch as well. So we're really trying to move towards doing that process in a real foundry. As you can see, here's a sort of a comparison between our clean room where, someone like me standing there and then a commercial foundry. Okay, so I didn't talk about anything quantum about that light source, and the question is, will it ever be quantum? And the answer is, we don't know yet if these silicon emissive centers can emit single photons. There's more emissive centers than just the W centers that can be investigated, part of the reason they haven't been investigated more is because they emit at long wavelengths where silicon APDs, the traditional detectors people use, don't work. But when you have these superconducting detectors now, it opens you up to investigating these longer wavelength emissive centers. And if that really doesn't work, we know that 3-5 electrically injected single photon sources are possible. But even with those, there's more work with quality issues. Basically, the photons that they emit are not always indistinguishable, and especially when you electrically inject them, they're not indistinguishable. But that's still an area of active research that people are really working on improving these kinds of sources as well. So then, let's bring it back one more time to the Bell experiment example. For that experiment, you need an entangled photon source on chip, not just a single photon source. So really, from the current state of the art, these nonlinear, pump sources are the best bet. but scattered light from the optical pump is still an issue with those. It's by no means solved technologically. And like I said, the electrically injected sources usually have worse quantum properties. So that brings me to the conclusions of this. I'll have a few more comments after this, but you know, essentially on the detector side, superconducting nanowire detectors, they can do very efficient single photon detection. They're already being used in a lot of quantum optics experiments, and they work well on waveguides as well. For the integrated optics, one of the main messages, you know, coming out of this talk is that really that no one material platform satisfies all the needs, and so integrating different materials together is really necessary. And that, you know, integrating quantum sources and detectors together really remains an open research question and remains challenging. So the last thing I want to say is that if you have all this technology, you can do more things than just quantum optics with it. And at NIST, we do a whole bunch of other things. You know, here are a couple examples: mid-IR spectroscopy, you know, on-chip nonlinear optics, dark matter detection, and then the one that I'm going to highlight for the next 5 minutes, which is the neuromorphic computing platform. So the big advantage of the neuromorphic computing platform from a technology point of view is that there are no quantum requirements. It uses all the same elements, but we don't need quantum sources. And the detectors are also relaxed. We don't need single photon detectors, just few photon detectors. And so what is neuromorphic computing? It basically means trying to build hardware with the capabilities of the brain. Now, if you want more on this, you'll have to, you know, invite me back for a second colloquium some other time. But I'm just going to give you like the 1 minute overview here. So the idea is basically that, you know, part of the reason that the brain has such unique cognitive and processing capabilities is actually down to the hardware in the brain, and it's really hard to emulate on current hardware systems, current electronic systems. And so we've been designing a hardware platform that uses a lot of the elements that I've talked about today, things like multiplanar waveguides for routing. So the idea is that in the brain, one neuron can be connected to over 10,000 other neurons. And so optics is a really good way to do that. It uses superconducting detectors for the optical to electrical conversion. If you're going to signal with light, light is great for communication, but we want to use electronics for computation, and so you need to convert between the two. And then there's a couple other superconducting elements that I haven't talked about. And then the LEDs, the silicon LEDs that are not quantum light sources, but are great for this. They're just LEDs for producing optical pulses. And so the basic idea is that if you have an integrated fire neuron, you basically exceed the threshold in the neuron and it fires an optical pulse to thousands of other neurons. And so the thresholding element we're using is the superconducting to normal extreme nonlinearity. And so when the superconductor, you know, you have a superconductor in parallel with an LED. When the superconductor goes normal, it diverts current to an LED and you emit an optical pulse. And this can go down a series of branching waveguides. Here we show a 10 to 10 neuron connection in the multiplanar waveguide materials platform. So then the vision is really, you know, first and foremost, is to try to understand the hardware in the brain, but ultimately you could imagine using something like this as an accelerator in a computer, similar to, you know, you have your quantum accelerator and you have your neuromorphic accelerator, you know, in some kind of supercomputer. So with that, I just want to finish up and thank the team at NIST. Obviously, this isn't all my work, and I would be happy to take any questions.
Thank you, Sonia, for a very interesting talk. So we will be in the question session, and if you have any question, please raise your hand, and I will unmute you, and you can ask your question. See. Okay. Mo?
Yes. Hi. I'm Obi. Can you hear me?
Mo, we cannot hear you well.
Okay.
Now it's better.
Yeah, I'll speak louder. So one of the questions about the chip concept, you show that if everything on the chip, right? So that I suppose you envision for quantum computing application, right? Because otherwise for quantum communication, that if you don't, signal has to go off the chip and over a long distance, right? So it doesn't make sense putting all the waveguide on the chip. Could you say something about such a integrated photonic platform for optical computing? What's the perspective there?
So I'm sorry, Mo, I had kind of a hard time hearing, but I think what you were asking is, you were pointing out that there are some quantum optics experiments, things like probably quantum key distribution, where you don't want it all on a chip, and one of the main ones where you want it all on a chip is quantum optical computing.
Yes.
So yeah, linear optic quantum computing. And yeah, this kind of technology is definitely applicable and interesting for that. So for that, you need to generate a lot of entangled photon states. You basically need to do all the same things I was talking about, but many more of them. You need many entangled photon states to, those are your qubits essentially. At NIST, we've been more focused on quantum optics experiments, things like I said, the on-chip bell test for certified random number generation. But there are, companies and so on, like I think, working on linear optical quantum computing, trying to implement some of these technologies for that. I don't know if that was answered your question or not. I'm sorry.
It's pretty fine. Yeah, and the Psi Quantum recently raised $265 million. I just saw in the news. Eric?
Yeah, can you hear me?
Yes, I can hear
Yep.
you.
I was just wondering to what extent the devices that you're making and characterizing have been simulated and modeled, and is there a role for that? I understand, of course, that the modeling would be incredibly complicated, but building a simulation and a model of your device before you built it, of course, would be good.
Yeah, so we simulate and model all of our devices before we build them. That's the typical procedure. Is you simulate it, you fabricate it, you test it, you compare it to your simulation, you figure out why it's different. So the thing is, it's hard to fabricate exactly what you simulate, I guess.
Yeah, so I guess, is there like a feedback loop where you build something, you refine your models, and then if so, what are the kinds of things that help with that process in terms of modeling, or is it always going to be sort of empirical?
No, what helps is so if you had a really standard process, you design it, you fabricate it, you test it, maybe you add some test structures that give you more information about things like loss and so on. And you could, if your process was exactly the same every time, then you could be very, very good at modeling it. And I think that's one of the main drivers for trying to move to a integrated photonics foundry, is that their processes are very reproducible. The real issue occurs when I make a wafer and then I wait 6 months before I go back to the clean room and fabricate another wafer, and now something's changed and it's again different. So I think it's kind of a problem of small clean rooms almost. There are other problems, but I see that as one of the biggest problems is, things are constantly changing in this kind of academic clean room or, government lab clean room. Yeah.
Great, thanks.
Is there any other question? So when people are thinking, let me just ask one simple one. this neuromorphic computing that you guys are doing, is it DNA or spiking based neural network? What's the neural network model or neuromorphic computing model you guys are trying to implement?
Yeah, it's spiking. It's a spiking neural network model.
It's like
so,
what
yeah.
Professor Paul Pracknell from Princeton doing, similar to that?
I mean, I think Paul Pracknell at Princeton is doing several kinds of neuromorphic computing. I think they're one of their main ones is not spiking. Actually, I think we might even have Alex Tate around to answer your questions more about that. But I think the main silicon photonics neuromorphic computing platforms that have been proposed are not spiking and are deep neural networks.
But you guys are looking into spiking, like in.
But
in
we're
NIST.
looking into spiking. That's
Okay.
right. At NIST, we're looking at spiking. Yeah.
Well, I'll just jump in. I don't know if you can hear me. This is
yeah,
Alex.
I can hear you, Alex. Yeah.
So it's a split. I think there's kind of a division of some architectures looking at spiking in silicon photonics and some that are not. And there's spiking is kind of, it's the potential for better processing potentials, but it's harder to integrate because it involves lasers and 3.5.
Yeah.
Unless you're cryogenic, then you can have silicon light sources like Sonia talked about.
Yeah. Yeah. Okay. Yeah. I think then we can, if there's no other questions, we can thank the speaker by clapping in Zoom. And yeah. So yeah. And so should we, Mariam? How do you close it? Just in the meeting? You're muted, Mariam. Yeah. Yeah. So.
Yes, I also wanted to thank Sonia for the great talk, and yeah, see you all next week for the next Colloquium talk on Tuesday. Check the Colloquium website for the schedule and check the course Canvas page for attendance details. Thank you very much.
Thank you.
Thank you. Bye-bye.
Thank you.